Hi, in this video we're going to pick up where the last video left off and start talking about how to deal with some of the trickier situations that can come up in our double integrals over general regions. So, one type of example would be if you're just given points where evaluate this integral over region D over of 4x cubed dA, where D is the triangular region bounded by 0, 0, 4, 4, and 6, 0. Okay. So why is this one trickier? Because now you are the one responsible for coming up with some equations here. So we're going to draw the picture in our 2D plane with 0, 0, 4, 4, and 6, 0. It probably shouldn't look as symmetric as I've made it. And when I look at that, do I think it's a type 1 or type 2 region? Is it easier to go top bottom first or left right first? And I hope you notice that if we go top bottom, we'd have to use two different regions. We'd have to use two different integrals to describe the left half, so to speak, where the top is this positive sloped line, and a different situation for the right half, where it's this negative slope line on top. So this is one situation where we want to definitely use our x values first, where I want to go left-right, because no matter where we are in the region, our left-right region is pretty clear. Our left-right limits are clear and are the same. So if I'm going left-right first, I'm going to do 4x cubed. Left right first would be a dx, then a dy. Because I'm trapping the x values first, then I'm going to handle the y stuff. And that means it's also easy to see because we already know where that point is, that we're going to go from 0 to 4 on our y surface. All that's left is to decide what these linear equations are. Now, because we're used to doing this in terms of y equals, you could probably find these line equations in a number of ways. So for instance, this line should be y equals, you should pause the video right now and try to figure it out on your own. It's negative 2x plus 12. This line is even easier. It's just y equals x, right? They have the same coordinates, both points. So if we want to switch it and make x the solved for, this left line is easy. X equals y. This right line takes some solving, right? You'd have to get x equals, it's going to be negative 1/2 y minus 6 plus 6 plus 6. And that's just how you do it. And we want to make sure we use the right side as the top bound, negative 1/2 y plus 6. And the bottom bound should just have y in it. Now, again, I know that's confusing. These are the x bounds, though, and that's why we're doing x first. So our first pass of the integral should be x to the 4th, evaluated from y, x equals y, to x equals negative 1/2 y plus 6. Then a dy. We'll have all the x's gone at that point. And then the scary looking expression, but it's actually not that bad. It's not as bad as it could be. That to the 4th power minus y to the fourth, all evaluated from, dy. The reason it's not that bad is because this one, either through u substitution or thinking about the reverse chain rule, is pretty easy to get the correct coefficient, the correct reversing of the chain rule. So we're going to have 1/5 and a -2 to the 5th power. Add 1 to the power, multiply by the reciprocal. You should check that with all the hook-ons. That makes sense. Minus 1/5 y to the 5th, 0 to 4. And of course, that's where it's going to get a little wild. It should be -2/5 4 to the 5th minus 1/5 4 to the 5th minus, plugging in 0 does not give you 0 here. That's the kind of thing you want to check out for. -2/5 6 to the 5th minus 0. So, not a nice number. Not going to spend time simplifying that. But the main takeaway is you would not want to do this as a type 1 region. The region itself can force you to choose which kind of problem you're doing. A similar situation to all of this would be a problem like, find the volume of the tetrahedron. A tetrahedron is just a four-sided solid. So, yeah, four-sided solids, that's correct. Bounded by the planes, not like a four-sided shape like in 2D. It's a 3D shape that has four sides only. It's like a 3D triangle. It's kind of a pyramid, has four sides. Pyramids are types of tetrahedrons. X plus 2y plus z equals 2. X equals 2y. X equals 0. And z equals 0. Okay, so one thing we want to do is one of these is going to be what we're under. One of these is easily seen to be what we're under. And that should be the one that has all three variables. So we're going to be under this. It has all three variables. Particularly, I can solve for z in terms of the other two. And that gives me a good f of xy. That's going to be our integrand. Now, how do I do the rest of this? We want to make sure we project into xy plane, because we want to see it's under that region, it's above z equals 0. That's the z equals 0, that's the xy plane. So we want to see what this looks like in the xy plane. What kind of shape are we getting in the xy plane? In the xy plane, we're going to make z equals 0. That has no effect on this equation. No effect at all on that equation. X equals 2y is, careful, it's going to be a shallow sloped line. It's not y equals 2x. X equals 2y, right there. X equals 0 is our y-axis. And you might be saying, well, wait, I don't see what else to do here. You have to go back and check out your original guy. We need to check 0 equals 2 minus x minus 2y. Or rather, if you wanted to think about how to graph that, it would be easiest to see it just solve for x, though. 2 minus 2y. But in terms of graphing it, be y equals 1 minus 1/2 x. And that would be the equation like. So another triangular region. A lot of students have trouble shading because you can see, oh, like this is all three. No, it's not. That does not use x equals 0, right? If I shaded this would not really use this as one of the boundaries. So please make sure when you're shading, you're always picking the region that has all three boundaries as its sides. Unlike the last problem, this is pretty clearly a type 1 situation. So it's good that I solved this one for y. I'm going to solve this one for y, no big deal. Because we're going to want to do top minus bottom first, which means we want to do the y's first. So my volume is going to be f of xy, 2 minus x minus 2y, d, we're doing the y's first because it's easier to look at top minus bottom. I'm going to pause it and let you try to take this the rest of the way. You should be able to come up with the bounds in both directions. 3, 2, 1. The lower y bound is clearly that red line, which is y equals x over 2, to our higher bound, which is y equals 1 minus 1 half x. For our x bounds, we want to make sure we are using our sense and solving for their intersection right there. If we have x equals 2y and I have x equals 2 minus 2y, then I have 2y equals 2 minus, then I have x equals 2 minus x, or 2x equals 2, x equals 1. Now, why did I switch tracks there? I wanted to find the x value. It's 1 comma something. It's 1 comma 1 half. We can see from both equations. But I want the x value because I want to know we're going from x equals 0 to x equals 1. And that's my setup. Now, I hope you all took the time to try to do this problem. It gets a little hairy. 0 to 1. We're going to integrate with respect to y's first. 2y minus xy minus y squared. We're plugging in the y's. Be very careful how you're plugging things in. Then we're going to do dx at the end. So I'm getting 2 minus x times, we'll just do x times plus x squared over 2 minus 1 minus x over 2 squared minus parentheses x minus x squared over 2 minus x squared over 4. And all of this is against dx. It's just with respect to dx. You should double check that you and I are on the same page here. And I'm going to shrink things and we're going to get to the next step. I'm going to simplify this. Off screen, I got the integral from 0 to 1. That's not going to change. X squared minus 2x plus 1. So make sure when you simplify it, you can get that. When we integrate that, 1/3 x cubed minus x squared plus x from 0 to 1. When we plug in 0, we get 0. So it's negative 1/3 plus 1, minus 1 plus 1, or it's just positive 1/3. The last kind of tricky thing that can happen here is the following. They can give you an integral that's just innocently sitting here, 0 to 1, 2y to 2, e to the negative x squared, dx dy. So notice, this is an integral that commits you to doing x first when it's already written in iterated form. This integral is committing you to doing x first and then y. Now, you might be like, oh, well, that's easy. They just told us how to do the problem. The hard part was writing it as iterated, and they tell me how to iterate it. Well, then think about this. How are we going to integrate this? What is the antiderivative of that function? Now, there are techniques you can use here, but in general, this integral, the integral of e to the negative x squared dx, is an impossible antiderivative to do without a lot of hard work. So, instead, we want to, and here's usually the instruction you get, evaluate by reversing the order. Now, how can I possibly reverse the order? First, notice that these are x bounds. And of course, that would mean these are y bounds. Make sure you're clear about why that's the case. Then we're going to draw the region that that's describing. Now, my region says if x is supposed to go up until x equals 2, and we're supposed to start with x equals 2y, it's a lot like the last one we just did, it would be a line. You can use solid lines, I don't know why I'm switching. Y equals 0 is, of course, the x-axis. Y equals 1. And which region are we talking about here? Well, it can be really hard for students to tell because, like I said in the last problem, you want to make sure you're picking the correct region, that you're shading the right region. So literally go in the order they tell me to. I want to start from x equals 2, y, and go to x equals 2. Starting from x equals 2y, go to x equals 2. And we're going to add those slices from y equals 0 until y equals 1. Hopefully you can see why it would be that lower triangle here, not any other triangle. I want to reevaluate this into a type 1 region. A type 1 region where I go top to bottom first. And in this case, well, we know what we would do here. Switch that to y equals x over 2. And we're going to go to y equals 0. So y equals 0 to y equals x over 2 would now be our innermost integral. And we're doing y first and then x. And what would that make the x bounds? Well, my x bounds are going to go from 0 to 2. I want to add up these lines starting from 0, 0 and stopping at x equals 2. And you might say to yourself, why is that any better at all? I don't get it. Why would we want to do that? Why is that good? Well, it's good because by having us do y first, I can treat this whole thing as a constant, meaning I can actually integrate and get e to the negative x squared y, evaluated from y equals 0 to y equals x over 2 dx. Again, if you're not convinced, just hang on. So that'll be 1/2 x e to the negative x squared dx. Why is that any better? Because now, unlike before, if I made a u substitution with u equals negative x squared, or if I just looked at the reverse chain rule type approach, the derivative of that exponent is 2x, and now I actually have the x I need to do the reverse chain rule to do the u substitution. So this would become 1/4, a negative 1/4, e to the negative x squared from 0 to 2. And if you don't believe me, double check by taking a derivative here. So it's a negative 1/4 e to the negative 4 minus, careful plugging in zeros, not a 0, sorry, minus a negative is going to be a plus, e to the 0, which is just negative 1/4, e to the negative 4 plus 1/4. Ta-da! So it takes something that's impossible to something that's really is possible. We're going to lengthen this video. We're going to do 2 more examples, and then we'll be done. 0 to 4, root x to 2, sine y cubed dy dx. And again, same instructions. You're going to be evaluating by reversing the order. It should be clear to you why you would need to reverse the order here, because this integral is not doable. So we're going to draw a picture. You should draw the picture and do your best to reverse the order of integration and get us an integral that is doable because you're doing it in the reverse order. Start by drawing, then try to find the bounds. 3, 2, 1. So we're talking about y equals root x to y equals 2. I know what that looks like. Y equals 2 is somewhere up there. Y equals root x goes like that. And we're talking about going from the top to the bottom. And we're going to talk about moving that from left, 0, x equals 0, to where they actually intersect, x equals 4. But that's not doable. So can I switch this? Can I switch this to be talking about from right to left? Yes. All it takes is redefining this to be x equals y squared. This still x equals 0. So 0 to y squared. And then we want to think about how are we going from top to bottom. From bottom, our bottom y is 0. And our top y is 2. 0 being the x-axis to 2. So if you, oops, and then we're doing x first. Very intentionally, we're switched the order. So these two are the same. This is the Fubini's theorem we were talking about. So try this out. See what happens. See what you get. 3, 2, 1. The reason this is better is because now this just becomes a constant. X equals 0 to x equals y squared. And so we can do our first integral, and that gives us hope, because when I plug in that x, I get y squared sine of y cubed, which is a much more doable integral. Specifically, we can use the reverse chain rule or use substitution to get 1/3 cosine y cubed negative from 0 to 2. So negative 1/3 cosine of 8 minus or plus 1/3. There's one more example in the book, but I think this video is already getting a little long. So I would recommend taking a look at that. And of course, as always, doing the homework. Thank you for your attention. I'll see you in the next video where we'll talk about how polar factors into all of this. Bye.